Similar with symmetrical parabolic vertical curves, there is a different set of functions to solve for the elements in unsymmetrical curves. Learn how they were derived here in engineering surveys. The approximate approach of curve fitting needs to minimize the errors, if not zero it out. And with this method, the concept is to have the positive errors balance out with the negative errors so they can cancel out. Since there are two different partial lengths in the curve, the first element is to locate PVI, which could be stated as looking for L1 from PVC. By using similar triangles, we can take the ratio of L1 with 2H. This is proportional with the bigger triangle, where we get the whole length of the curve, which is L1 plus L2, as to the whole height in the triangle, as L2 times the algebraic sum of G1 and G2. Take note that G2 is negative. That is why it turned out as G1 minus G2. Cross-multiplying the two terms, we get L1 with L2 times G1 minus G2. Then, this is equated with 2H times L1 plus L2. Simplify terms on the right to have 2H with L1 and 2H with L2. Now, transpose 2H L1 to the other side. Next is to extract L1 from the binomial, making the function L1 times the binomial L2 with G1 minus G2 and negative 2H. This large binomial is placed to the other side to isolate and have the function for L1. When solving for vertical offsets, the same concept will be used. The tangent and the curve are involved, so instead of using similar triangles, similar parabolas will be employed. Ratio and proportionalities with the squares of distances, so the same can be taken from unsymmetrical curves. That is, the square of x is to y as the square of L1 is to h. Next is to derive the function for the highest or the lowest point in the curve. Since unsymmetrical parabolic curves are like compound curves, we consider just one and treat it as a symmetrical curve. The common tangent of the curve is now labeled as G3, so all elements are clear. Now recall the derived function for computing the location of the highest point. The function from the other curve is S1 as equal to G1 times L all upon G1 plus G2. G2 here is taken algebraically, or that is including the sign. Since the length of the curve is now tagged as L1 and G2 is now replaced by G3, the function for S1 is transformed into G1 L1 over G1 plus G3. We already have the S1 function, but the problem is we don't know what G3 is. But using the triangle, we can then have the lower part as G3 times L1 over 2. Then the other one above is G1 times L1 upon 2. The derivation of these are similar with how the symmetrical curve distances are solved. Take the total height from these two and get G1 times L1 over 2 less G3 times half of L1. Factoring out half of length 1, we get L1 over 2 times G1 minus G3. Now we can equate the two distances. We then have h is equal to half of L1 times the quantity of G1 minus G3. Then we write this as 2h is equal to L1 times G1 minus G3. Take out groupings and distribute L1 to G1 and G3. Then isolate the term with G3 to have L1 G3 as equal to L1 G1 minus 2H. Divide everything by L1 and get L1 G1 minus 2H all over L1. Simplify each term to have G3 as G1 minus 2H all over L1. With the previously derived S1 formula, we can now plug G3, which is G1 minus 2H over L1. S1 then becomes G1 L1 all upon G1 minus the new G3, which is G1 minus 2H over L1. G1 then cancel out to have S1 as G1 L1 upon 2H over L1. Place the denominator of the denominator up to have S1 as G1 L1 squared over 2H. In similar pattern, we can deduce the function for S2 to be G2 with the square of L2 upon 2H.